All right, welcome back, guys. So, I want to pick up right where I left off last time in our discussion of energy. And what we had discussed is that there are two ways energy can transfer. And those two ways were heat and work. Now, today's lecture is going to be on heat. Before we get to that, I want to add one note. When we talk about these two ways that energy can transfer, on this list, we aren't including mass transfer. But I want you to remember that mass is technically a form of energy. That's something that Einstein told us. Energy and mass are equivalent. And so if we have an open system, remember our definition of an open system, it's something where energy can transfer and mass can transfer. And in that definition, we've differentiated the two. For the purposes of this class, we're going to differentiate the two, all right? And so we can always have mass transfer, maybe we have an open system. When we're talking about energy transfer here, we're talking about energy that is not in the form of mass, okay? So energy that uses the definitions with which we've defined open, closed, and isolated systems. So with that out of the way, we have these two forms of energy transfer. And like I said, today's topic is heat. So in physics, we use the letter capital Q to denote heat. And so it might be nice to first talk about what the heck do we mean about heat? What is the definition of heat and what does it look like? So first I'll write the definition up. And heat is a transfer of energy from a temperature difference. So what this means is that in any system where energy is being transferred in the form of heat, you're going to have one system or side or partition that has a higher temperature than the other. So if both compartments or systems or whatever you're comparing, if both of them have the exact same temperature, then there can be no heat between them, okay? There can be energy exchange still in the form of work, but the category of heat, we must have an energy or a temperature difference, all right? Now remember, the transfer of energy is the heat, right? So if I say heat transfer, I'm saying the same thing twice. I don't need to say heat transfer. When I say the word heat, I'm talking about a transfer. A lot of times we don't speak this formally in the English language. For example, I might talk about my body heat. Now, I don't really have a body heat. What I really have is a body temperature. Heat implies that I have some sort of transfer of energy, energy leaving or coming into my body, all right? When the energy is inside me, it's just internal energy, okay? There is no transfer going on, and thus there's no actual heat. But because scientists have formalized this and understand this so well, usually they can even use this colloquial language, body heat, other terminology that's not technically correct, but they can do it without getting confused, okay? But I want you to understand that, and this is a good idea to throw up again. If I have a system, energy is what's in the system, right? Heat is an arrow, okay? Heat is not what the system contains, it is the flow, okay? So when we talk about transfer of energy from temperature difference, I think that we should define some terms having to do with temperature difference. So the first term that I'm going to throw up here is thermal equilibrium. Now, we remember talking about equilibrium from our discussion of processes and states on our PVT surface. And what we formally defined it as is when the state of the system has a point that lies on the PVT surface. And we talked about how if the point is above or below the surface, we are not in equilibrium. Well, this is similar to that, but it's thermal equilibrium. So we're talking about a specific type of equilibrium. And remember from our first lecture on terminology, thermal has to do with temperature. So what thermal equilibrium between two systems is it means that I can have system A and system B, and these are full of particles, right? A fluid or a gas or solids or whatever they are. And I can have them next to each other, and there is no temperature difference, and thus there's no heat flowing, right? Heat is transfer of energy from temperature difference. So, if these two are in thermal equilibrium, no heat can flow. And so that gives us a definition of thermal equilibrium. And I'm not going to do a fancy definition. I'm just going to write same temperature. Okay? That's a layman's definition for what thermal equilibrium means. Now, I'm going to take this part of the lecture to introduce one of the laws of thermodynamics. So, this is the 0th law of thermodynamics. Now you might say, why 0th? Why not just start it first? The reason for that is that there are 4 laws of thermodynamics, and historically what happened is people came up with the first, second, and third ones. And then, after those, they realized, oh, there's another law. But that law is a lot more fundamental. It's a lot more simple than the first 3. So we don't want to call it the 4th law of thermodynamics. We want to go back before the beginning and lay it down as a foundation. And so they went all the way back past 1 and called it the 0th law. Okay? So this law is really foundational. And because it's so foundational, it's very obvious. Okay? It's simple to understand. But it's going to take me a while to write. Okay? So if I have 2 systems, like I've drawn here, this system's A and B, and then let me have 2 more systems. So actually, I'm just going to tack this on here. System C, okay? So all 3 of these systems in this example are in thermal equilibrium, and we're going to formalize that when we write this law. So if system A is in thermal equilibrium with system B, and system B is in thermal equilibrium with system C, then system A is in thermal equilibrium with system C. So, I'll let you read that now that I've taken the time to write it out. Understand how simple this is. What we're saying is, if there's no temperature difference, aka no heat flow, aka thermal equilibrium, between these 2 systems, and there's no temperature difference between these 2 systems, well then, there's no temperature difference between these 2 systems. All right? The presence of a middle system that they're both connected to guarantees that they're both in the same thermal equilibrium. And this is the principle of how we can check different things and compare them using a thermometer. replace system B in the middle with a thermometer. And we measure system A, and we say, okay, system A and this thermometer have come into thermal equilibrium, and we've measured that temperature. Now, system C and that thermometer have come into thermal equilibrium. And if they're the same, B and A are the same, they agree, B and C agree, well then we know, oh, A and C therefore must agree, okay? So this is, again, if you think this is trivial, you're right. If you're like, what is so deep about this? Don't worry, you haven't missed anything. It's not that deep, okay? It isn't, but it's pretty simple to understand this law. Zeroth law of thermodynamics. Okay. Now, remember that we talked about when we gave the definition of temperature, how it's closely related to energy. And we can already see that in what we talked about. Somehow there's this connection between a temperature difference or thermal equilibrium or not, whether or not there is a temperature difference, and whether or not heat can flow, which is the transfer of energy. So what is the connection between energy and temperature? I think that's interesting to talk about for a minute. And what I'm going to write down is something that's very familiar to you. This is our ideal gas law, right? PV equals some number times the temperature. And remember that whole lecture that we basically spent talking about all the different ways of writing down this number. Well, it turns out that this side, that's just an energy. So I can write this as an equation that simply says the energy is equal to some number times temperature. Look how close they are to each other. It almost says energy equals temperature, right? It's just this factor of a number in there, but that's just a number. So energy and temperature are really closely related. And for the most extent, in most cases, you can just measure the energy of a system based on its temperature. Higher the temperature, higher the energy. And that really comes into play when we try to look at what is going on at the molecular level when we have heat transfer. So this is true for each molecule, right? So, and remember, I should say, we're not defining a temperature on an individual molecule. We're defining a temperature as a property that a collection of molecules have. What are they all doing in relationship to each other? And we talked about that in our lecture on temperature. So imagine that I zoom in to that chart that I drew with system A and B, and I want to zoom in and see what's happening there. So here's, let's say, our dividing line, and we've got this completely sealed off. But now let's pretend that they're not yet in thermal equilibrium. There is a temperature difference. One side is hotter than the other side. So on the cold side, we know that we've got these molecules and they're squiggling around, all right? They're going around in little circuits, they're sort of wandering. They're not all going in circles, but they're quivering just a little bit relative to each other, and they're moving just a little bit relative to each other, okay? This is just a review of what we've talked about. Then we go to the hot side, and we've got big things like this, where things are quivering quite a lot, and with respect to each other, they're also moving quite a lot. They're going in these big paths around. So these have more energy than these. And so you see the direct correspondence between energy and temperature. Hopefully this is all review for you. Now, this is not in equilibrium because there's a thermal difference between them. Okay, there's a temperature difference. If I now break down this wall, what do we know from our law will happen? If there's a temperature difference, then bingo, heat will flow. So, if I break down this wall, let me get my red marker to represent heat. Heat is going to flow across this barrier. Now notice I've drawn all the arrows in the same direction. And that's important. Energy in the form of heat will always flow hot to cold. And there's a really, really fundamental reason why this is true. We're going to touch on it when we get to the second law of thermodynamics. That's going to be in a few more lectures. But the key point is this arrow does not go both ways. Cold can never flow toward hot. It's always hot to cold. Look why that is. These molecules that have the big, wide, sweeping paths, well, they are going to get swept into here, right? They're going to wiggle over to this side. And what that's doing macroscopically is this side is heating up. Whereas these little ones, they don't have a lot of interest in going over there. They're just wiggling in their little circuits. There's no energy propelling them to the other side. And so what happens is that these molecules that have a lot of energy transfer some of that energy to the molecules on this side. And there's 3 different ways that that transfer can happen. So I want to draw a really exact picture of each one and try to show you what's happening. So first, we have conduction. And the book doesn't give a very, very formal definition of conduction. There is one, but I've decided to just take the same route and talk about these as general principles and give you somewhat of an idea of what's going on. Try to draw for you an exact picture, but not a formal definition. So I'm just going to write a really simple definition up here, which is that the particles bounce. So what do I mean by this? They collide with each other. These super energetic particles are whizzing across that barrier now that it's been broken down. And here's my lazy, well, I'll do it how the picture is. Here's the fast ones, here's the lazy ones, just kind of wiggling around in small little orbits. And this one comes in and they can hit them. And when it hits the ones with lower energy, that sends them off and gives them a higher energy. And so microscopically, that's what's happening. Let's say this little guy and this one comes in, hits it, and it bounces and goes off with a much higher energy. So our simplistic picture of this is that conduction means the particles are bouncing and colliding, and that's how they're transferring energy. Then there's convection. Convection is, I think, the hardest one to wrap your head around, but I think there's an easy way. Imagine that instead of these particles being stationary, there was a flow here, right? Imagine maybe this boundary was a pipe that you broke down, so that when you broke down the boundary, one half of this, it was all moving, it was all rushing this way. Well, as those highly energetic particles come across that boundary, they're going to get swept up in that current. And that's going to increase their energy on the other side of the boundary. So they're getting pulled along or swept up in the flow. And that's what I'm going to write for this one. That's the second way they can increase their energy. Their particles being pulled along. So I'll draw a sketch of that, like maybe down here. Right? It gets in there on over to that side and it gets pulled. That's convection. If you don't understand it completely, that's okay. Very few people do. So the last one is radiation. And this one brings in the concept, there's some principles from quantum mechanics that we're going to gloss over, but basically particles that have high energies can send out electromagnetic waves. They're little packets of energy. So it's like, I've got a lot of energy and then I send it out, like throwing a baseball, and then I'm able to calm down and have less energy. And that little packet of energy is transmitted through the electromagnetic spectrum. And so that's like shooting these little packets of energy over, and these ones getting it. So this side calms down and that side receives them and they get all amped up, okay? And so this radiation is particles exchange electromagnetic waves, okay, little packets of energy. So those are the three types of how this can happen, what this picture can look like, which admittedly is getting to be a messy picture. But the fundamental concept that all three have in common is that one side that's at a higher temperature gives energy to this side. And that is a picture of what heat is. Okay? Heat is the name for describing that process. All right, there's a few more things here that I want to talk about. You might remember that for normally when we have a quantity, and I'll just put our big version of our quantity. This is a capital X. This is whatever. X is equal to our quantity. We can always make a specific version of that quantity by taking the big X and dividing it by the mass. We use the lowercase letter, and we say that this is the specific version of that quantity. And we've done that for a few things now. So does that hold true for heat as well? Well, almost. So first, let's do that. Let's do it for heat. So remember that Q is heat, and if I take Q and divide it by the mass, well then what I get is obviously heat per unit mass. Now, unfortunately, that's what it's called. That's the only name for it. It's not called specific heat, not quite. The symbol for this is, of course, lowercase q, because we keep the same convention that we when we divide by the mass, we use the lowercase letter. Okay, so we still use lowercase q for this, heat per unit mass, but in order to get specific heat, what we like to do, or what was decided that we were going to do, is also divide by the change of temperature. And it kind of makes sense why we would do this, because we want a quantity, when we talk about specific heat, that not only depends on the amount of mass, but it also depends on the amount of temperature differential, right? If heat depends on temperature difference, well then we should put that in the definition of our specific heat. And so this is actually, let me see if I can spell, specific heat. It's almost the same as what we'd normally call specific heat, but it's just got this extra factor in the bottom of temperature difference. And we call this with a lowercase letter c, all right? Specific heat we are going to come back to because there's more to this story, but I just want to introduce it to you now. So this is specific heat. Notice that you can rearrange this equation. If I take m delta t and multiply both sides by them, I get a formula that looks like this. Q equals m times delta t times c. Actually, I want to change the order of these. Makes no difference, but it's typically written one way. And I'm going to see if I can box this up, because this is a relatively famous and useful equation that we're going to be using throughout this course. Okay? So just keep this vernacular in mind, and we're going to come back to it. Let's see. The last thing that we can define is we can take our heat and we can say that a specific amount of heat divided by a specific amount of time equals the rate of heat. Now, a lot of times people would write the rate of heat transfer, and our book writes the rate of heat transfer. However, remember, heat itself is the transfer. Heat is not a thing that's being moved, it is the movement of the thing, which is energy. So I'm just going to say rate of heat. If it confuses you, add the word transfer on, okay? And this is simply how much heat per unit of time. What is the change of time, or the time interval that it took? And there's a shorthand for that, which is Q dot. We just put a dot above it, and that means Q divided by delta T, okay? Spoiler alert, if we do the same thing for work divided by delta T, then this also equals W dot, we just put a dot on it, and this one, there's a specific word for, which is power, right? So rate of heat is to Q what power is to W. But we're going to get to this next time. Last thing that I want to talk about is this word. Adiabatic. Adiabatic is a fancy way of saying what we've said several times in this lecture, which is we've referenced situations where there's no heat transfer. See, I did it, heat transfer. There's no heat, right? There's no energy being transferred. That's all that adiabatic means. No heat during a process. Now, I want to be really exact, and I may have just misspoke a minute ago, I'm not sure. But adiabatic processes, does this mean no energy at all can be transferred? Not necessarily, because remember we've got two ways. We can still transfer over work. We can still have work to transfer energy. All adiabatic means is that there's no heat, okay? There's no transfer of energy due to a temperature difference, which is the definition of heat. So this will be a theme moving forward too. As we talk about processes, we will have processes that are adiabatic. And that tips you off, I know that Q equals 0 for that process because they tell me it's adiabatic, and that's what it means. Q equals 0. Okay? Next time, as I said, we're going to talk about work, so I'll see you then.